Hello student, welcome back to the course on optimization methods for civil engineering, and this is the last class of this particular course. And in today's class, so I will solve a problem using different methods. So initially I will describe the problem here, and then I will solve this problem using genetic algorithm, then using classical method, and then using particle swarm optimization PSO method. So, let me explain this problem and then I will go to MATLAB. So, this problem I will solve using MATLAB, but you can also solve this problem using R software. So, only thing is that you have to write the code and then you can use the GA package available in R or classical optimization package available in R or PSO optimization package, so that you can use to solve this problem. So, let me explain the problem. So, this problem is a welding design problem of a beam. So, this is the problem. So, this problem is design of welded beam. So, design of a welded beam. So, this is the welded beam here I have shown in this particular figure. So, this is the figure, and I would like to design this welding. Okay. The mathematical formulation of the objective function, which is the total fabrication cost. Okay. So, what I would like to do? I would like to minimize the total fabrication cost. Okay. So, this I would like to minimize, that mainly comprise of the setup, the welding labor, then material cost as follows. Okay. So, this is basically the total fabrication cost of this joint, and I would like to minimize this cost. So, objective function can be written like this. Okay. So, objective function can be written like this. So, here there are 4 design variables, okay, x1, x2, x3 and x4. So, where x1 is the thickness of the weld, okay. So, this is your h and that is your x1, and I have considered variable x1. Then L is the length of the welded joint. So, this is the length, okay. So, this is the length of the welded joint. So, this is your the variable 2, and the variable 3 is width of the beam, okay. So, this is the width of the beam, and variable 4 is thickness of the beam, okay. So, for these 4 variables I have to find out the optimal value, so that the fabrication cost is minimum, okay. So, this is a benchmark problem, and many researchers have solved this problem using various optimization method, including genetic algorithm, including classical optimization technique, including particle swarm optimization. So, here I have considered total 6 constraints. So, these constraints are taken in such a way that the shear stress developed is within permissible limit, or normal stress developed is also within permissible limit. So, altogether we have total 6 constraints. So, I am not discussing about those problem or those constraints here, but if you are taking all these into consideration, then I am getting total 6 constraints, and these constraints are defined here. Okay. So, these 6 constraints are defined, and lower limit and upper limit of x1 is 0.1 and 2, that means range of x1 is 0.1 and 2. Similarly, x2 is 0.1 and 10, x3 is 0.1 and 10, and x4 is 0.1 and 10. So, what I can say that lower bound, so lower bound here it is 0.1, then 0.1, okay, then all are 0.1. So, 0.1 and 0.1, okay, and upper bound here is that upper bound here is your 2, then 10, then 10 and then 2. So, this is my lower bound and upper bound. So, this problem has this particular details. So, where tau is the shear stress and tau max is the allowable shear stress, and this value is given, and sigma is the normal stress and sigma max is the allowable normal stress, that also given, and PC is the bar buckling load, and the bar buckling load is given here. Okay. So, this is the bar buckling load and that value is also given. Okay. So, this is in pound and delta is the beam end deflection, and these are the relation between shear stress. Okay. So, other relations are also given. So, I can find out what is tau x within using this relation. And similarly, the other equations are also given for r, then delta x I can calculate, and these are the value of z, e, p and l. So, length is given, that is your 14 inch. So, I can use this equation, to calculate the value of the constraint. Okay. So, I can calculate the value of the constraint, and this constraint has to be satisfied, is not it. So, this is the MATLAB code using classical method. So, here I have used f mean con. Okay. So, this is the f mean con function I have used, and what I have to do, I think already you have solved several problems. So, I have to define the lower bound, I have to define the upper bound, I have to define an initial point because I am using the classical optimization method. So, I am using f mean con algorithm. So, therefore, I have to define this initial point and then I have to define the objective function. So, this is the objective function, and here there are total 6 constraints and constraint is defined in this particular function. So, you just see all these equations are calculated here. So, all these equations are calculated here. So, we do not have any inequality equality type constraint. So, therefore, this is your null, and this is the value of z, e, p and l is defined. Then you calculate delta x, then PCX you calculate, then sigma x you calculate, then r, then j, then m, and then tau 2 and tau 1 you have to calculate, and after that I am calculating the value of tau x. Okay. And then tau max is given. So, this is the value, and then you define that C1, C2, C3, C4, C5 and C6. So, sigma is also defined here. So, I can define sigma here also. Okay. So, there is no issue. So, once you are calculating this one, so this function will give you the value of C1, C1, then C2, C3, C4 and C5 and C6. Okay. C6. Okay. So, you will get the, so this function will return the value of C1, C2, C3, C4, C5 and C6. Okay. So, this is in using f mean con, and then I have solved this particular problem using ZA. Okay. So, this is the ZA function, and then this is solved using PSO. Okay. So, particle swarm optimization, particle swarm, and this is again. So, this part is same. Okay. So, this part is your same, only thing is that I have defined this value somewhere here. So, in case of PSO, so I have to write the objective function code. So, we cannot define the constraint and objective function separately. So, what I am doing here, I am writing the objective function and then the constraint. So, if there is no violation, then it will return the objective function value. If there is a violation, it will return a very large value, so that this particular solution can be avoided. Okay. So, that we are doing. So, for that I am using if else statement. So, if there is a violation, then I am returning this value, and if there is no violation, then I am returning this value. So, this can be written, and this part is similar to what we have already defined. So, there are another version of this problem. So, there is another constraint, that is C7. So, you can see, so this is another constraint of this particular problem. And so, I have also solved this problem using the constraint 7. Okay. So, constraint 7 is defined here, and I can calculate the value of constraint 7. Okay. So, this is the code using classical method. Using classical method. So, I have used fmin_con here, and the second one is your ZA, okay, and third one is particle swarm optimization. So, third one is particle swarm optimization. So, let us solve this problem, or let us run this M file in MATLAB. So, let us go to MATLAB. So, this is the MATLAB, and let me solve the first M file, and this is your fmin_con classical method. Okay. So, I can copy this. So, here you can see that I have defined the lower bound, I have defined the upper bound, and this is the initial point 111. So, I have considered 111, but let us see if we change it, whether you are getting the solution or not. Then you define the objective function, and then you write the constraint function. Okay. So, constraint function. So, here as I said that, okay, so let me define what is the value of Z, what is the value of E, then what is the value of P, then L. So, I can define this tau max here itself. So, I can define here. So, all the parameters I can define here, all the constant value. So, I am defining all this. Okay. So, this is, so I have defined, okay. Then I have calculated delta x, then PCx, then sigma x, R, J, M, then tau 2, then tau 1, and finally I am calculating tau x. So, once you are getting that one, then you can define the constraint 1, 2, 3, 4, 5 and 6, altogether 6 constraint, and basically, and there is no equality type constraint. So, I am putting empty here. Okay. So, after that I can simply run this particular line, and this is your fmin_con. Okay. So, this is your fmin_con, and here this is the objective function. Then I am defining x not, then a, b, a equal t, b equal t is not there, then lower bound I have defined, upper bound I have defined, then nonlinear constraint I have defined, and I have also defined the option. So, in option I have set the tolerance limit, okay, change the tolerance limit to e to the power minus 10, then function tolerance this, then display iteration. So, I would like to see the iteration value, and algorithm also I can define, this is sequential quadratic programming SQP. Okay. So, you can also define the other algorithm. So, but here I am using this one. So, let me execute this one. So, before that I have to solve this problem. So, before that I have to save this file. So, this is problem 1. Okay. So, this is n.m. Yeah. So, now I got the solution. Okay. So, I got the solution, and you can see these are the iteration also, and finally I am getting the solution. Okay. The solution value is, the value is 2.38. Okay. So, I can check what is the solution, that x value. So, this is the solution, that x1 is 0.244, then x2 is 6.21, and this is 8.29, and this is 0.244, and the function value you can see, and this is the function value 2.38. Okay. And as I said, the other researcher also solved this problem and they also got similar solution. Now, let me see if I change the initial solution whether I am getting this solution or not. Okay. So, let me put it, suppose if I put 2 and if I, okay, no, this is basically this is 2. So, let me and this is I am putting 5. Okay. So, this is also I am putting 5 and this is 2. Okay. So, let me run it. Yeah, I am getting the solution this time also. So, this is not that sensitive to initial solution. Okay. So, okay. So, I am getting this is 2.38. Now, I would like to explain one thing. So, here I have defined the function here. Okay. So, this is the function I have defined. So, I can also write this function somewhere else. Okay. So, I can save this file as an M file. Okay. So, this is a function and let me save it. So, I will save it as contour okay. So, I am saving in a separate file. So, let me see whether it is working or not. So, it should work. So, if I execute this particular M file, okay, so it is working. Okay. So, I am getting the solution. So, therefore, what you can do for objective function or constant function, you can create a different M file and that you can call and it should be in the same directory. Okay. So, if it is on the same directory, so you can save as a different file also. So, here what I am doing, I am defining this is an M file. So, this is a function and the function name is contr okay, and the file name should be contr. So, this should be same, that function name and file name, and then this particular function will return C and C equality, and here I am using this one. Okay. So, here I am using this one and then basically I am running this particular function okay, to solve this problem using sequential quadratic problem algorithm using SQP algorithm. Now, let us solve this problem using genetic algorithm or PSO. So, let us solve it by genetic algorithm. So, I am just copying this one. So, this is the ZA. Okay. So, this is the ZA part and here everything is similar. So, what we have run during the classical method. So, M code is similar. So, only thing is that we are using genetic algorithm function. Okay. So, this is the function. So, this is the function. The function is ZA and I have defined some option here. So, here the constraint violation I have changed, then function tolerance I have changed, and I am also displaying the iteration and population size I make it 100 and maximum generation I make it 400. Okay. And then this is the objective function, this is the number of variable, then we do not have A equal to B equal to, lower bound upper bound we have defined, and then non-linear constraint, this is the non-linear constraint and we have option. So, this function is same as what we have used in case of classical method. Okay. So, let me run this thing. So, before that I have solved it. So, this is problem ZA. Problem ZA. Okay. So, let me, yeah. So, you can see that function value is 67, now it is 15. So, it should go up to 2.36. Okay. So, it is running so it will go up to 400 iteration. Okay. So, up to 400 iteration. So, as you have seen, so when I have applied the classical method, so you just see within 10 iteration of your classical method, so I got the solution. But here it is running still. So, this is up to 35 iteration, 36. At 36 iteration I am getting 7.91. So, I have to go up to 2.36. So, final value is 2.36, around 2.36. Yeah. You just see it is not reducing. So, the function value is not reducing. So, I am getting the same function value. So, in that case it may happen that we are not getting the solution here. Okay. So, we are not getting the solution. So, let me run this thing again. So, now it has reduced up to 4.2. So, in this case also it is I am not getting the solution and I got 4.22. Okay. So, let me see again. So, I did not get the solution. So, what I will do, I will increase the population size. So, make it 200. Just see whether I am getting the solution or not. Make it 120. Okay. So, I am not getting the exact solution using genetic algorithm. So, and use the C, it is taking lot of time to converge it. So, finally, I am not getting the solution, but if you are running it, so you may get solution sometime, but therefore, it is better to solve this problem using classical method. Okay. So, let me see whether I am getting the solution using particle sum optimization method. So, this is the code for particle sum optimization. Let us save it. So, this is using PSO. So, here I have defined this objective function, and then I have used the particle sum optimization. Okay. So, let me run this thing. Yeah, use the C, I am getting the solution. So, here you can see what is the solution. The solution is, yeah. So, I am getting, so this is not the exact solution, but it is a near optimal solution. This is 0.2372, and so solution, and this is 5.46. So, it should be 6.7, and this is 9.48. So, I am not getting the exact solution, but it is a near optimal solution. So, this is 2.44. Okay. So, let me run it again. So, let me check. Yeah, I am getting little bit better solution, but this is not the solution. So, let me run it again. Yeah, 2.46 again. Okay. Yeah, 2.39. So, this is what I got when I have applied the classical method. Yeah, this is 2.4. So, swarm size I can use, let me see actually. So, if I use 100, then what will happen? Yeah, 2.39. So, I should get around 2.36. .59. Yeah, 2.38. So, you just see when I have applied the particle sum optimization. So, I am not getting the same solution every time, because what is happening here that you are starting with some different set of initial solutions, and therefore, you are not getting the same solution. And apart from that, so we are not taking the gradient information here, and as a result, so you may not get the exact optimal solution, but you may get a near optimal solution of the problem. So, if you compare the genetic algorithm with PSO, so you can see that the PSO is much faster than genetic algorithm. Okay. Even in this particular case, so I am not getting the solution using genetic algorithm. So, but I may get it. So, if I am running it for maybe 10 times or 15 times, so sometime I may get the solution, but every time I am not getting the solution. So, that means this algorithm is not robust enough to get the solution in every iteration or something like that. Okay. But when your problem has more than one optimal solution, then you can use genetic algorithm, because at that time it will be difficult to solve the problem using classical method, and once you are getting a solution near the optimal solution, then you can apply the classical optimization methods. Okay. So, let me go to the second version of this problem. So, this is the second version of this problem and this is the MATLAB code. So, let me copy this thing. Okay. So, here I have used the classical method. Okay. So, this is the second version. So, we have another constraint 7. Okay. So, let me execute this one. So, let me see what is the solution, and this is the solution, and objective function value is objective function value is 1.69. Okay. Okay. So, yeah. So, I am getting this is the solution of this particular problem 1.69. Okay. Now, let me solve this problem using ZA. Let us see whether I am getting the solution for this one. So, I am applying ZA here. So, let me see. So, here I am plotting this fitness function versus generation curve, and you can see it is somewhere here. So, the base fit solution is 5.6. So, now it is 4.63. So, you just see the function value is not reducing, and here the base solution and mean solution is almost same. That means, the populations are saturated with the base solution and we may not get any improved solution, because crossover will not create any new solution. So, therefore, so we may not get any solution and this loop may be terminated. So, now you just see the best and mean solution is same. So, that means we are not getting any new solution. So, it will go up to 400 iteration, but the function value is not reducing. Okay. So, I did not get the solution. So, let me try one thing. So, let me delete this part because I have already defined this particular problem. So, let me delete this part. Okay. I am defining a different function. Yeah, so this function I am defining in a different file. This is one. Now let me save it. CONTR1. Okay. So now I will be using this function here. Okay. So this is one. Okay. So let me try. So I am not getting any solution. So just see. So let me check this. So now it is reducing 5.65. So let us see whether we are getting the solution here or not. it is changing, but it is changing very slowly. So, in this case also we may not get the solution when we have applied genetic algorithm. So, it will go up to 400 iteration. So, there is a small change, but actually it is not converging at optimal solution. So, it will stop when we will get stall generation of 50. Okay. So, we are getting 50, that is the stall generation, then after that it is the algorithm has terminated. So, this has been terminated. Okay. So, we are not getting the solution. We can run it again once, just no. So, we are not getting solution using ZA. So, let me try with the PSO method. Okay. So, this is the PSO. Problem to PSO. Okay. So, let me run it. Yeah, I am getting the solution. You can see. So, here this is the fitness function versus iteration. So, solution is around 1.7, so or 1.69. So, let me check this one. So, the solution is this. Okay. And yeah, 1.69. So, I am getting the same solution what I got using the classical method. So, you can try again, I think second iteration also I will get the same solution. Yeah. So, you can see this is the solution, okay, and objective function value is 1.69. Okay. So, when you are applying this algorithm, so we have learned a lot of algorithms here, the both classical methods as well as non-classical methods. So, it is not that all the algorithms will be equally good for your problem. So, you have to find out that what algorithm you should apply for your problem. So, depending upon what type of problem you have, suppose as I said that if your problem is a convex problem and you just apply the gradient based method. So, easily you will get the solution of your problem. But if your problem is a non-convex problem, so in that case initially you can apply the meta-heuristic optimization method, and all the meta-heuristic optimization method may not be suitable for your problem. Suppose in this case we have observed that when we applied ZA, so we did not get the solution, but when I did some test run myself, so I got the solution of this problem, but during this live demonstration, so I did not get the solution. Probably if I am running this particular ZA maybe for 10 times or 15 times, so I may get the solution, maybe one time or two times I may get the solution, but most of the time I am not getting the solution of this problem. So, that means for this particular problem ZA is not a robust algorithm. So, what we have observed that when we have applied ZA, so I did not get the solution. So, that means for this particular problem ZA is too slow. So, it is taking lot of time, so lot of iteration, and after that also I am not getting the solution of this particular problem. But when I have applied the classical method as well as particle sum optimization method, so I got the solution of this problem. So, that means the PSO method as well as the classical optimization methods are quite good for this particular problem. So, therefore, the practical application is quite difficult, because you do not know what is the optimal solution of your problem. Suppose you have a problem of 100 variables. So, you will not be able to plot this problem. So, and you do not know what is the exact optimal solution of this problem. So, how many optimal solution you have, that also you are not aware. So, in that case this is quite difficult. So, what you have to do, you just apply the algorithm, and you can just report, or you may report that the known best solution of this problem is this, because you are not aware there may be some global optimal solution that you have not actually you did not get that solution. So, there may be a global optimal solution, and probably you are not aware of that particular solution. So, you can report that the known best solution of this problem is this. So, these are all benchmark problems. So, I know the solution. So, this problem can be used for testing your algorithm, and basically you can see. So, when I have tested the algorithm like classical method and particle sum optimization, so these two algorithms are performing well, but when I have applied genetic algorithms, so for this particular problem I did not get the solution, or I did not get a better solution. Okay. So, this has to be considered when you are applying optimization for a real world problem. So, this is all about for today's class, and as I said this is the last class of this particular course, and I discuss different algorithms. Please go through this algorithm and try to solve your problem applying this algorithm. So, you can write your own code. So, if you are willing to do that, you can develop your own code for implementing particle sum optimization, genetic algorithm, then classical optimization. But if you do not want to do that, and this will not be easy also. So, you have to write a very nice code to implement this algorithm. But if you want to do that, you can do it. Otherwise, the algorithms available in MATLAB or in R, so that you can use. And for smaller problem, okay, so you can also use Excel solver. If you do not want to write any code, okay, or do not want to use either R or MATLAB, so in that case you can solve your problem using Excel solver. Okay. So, thank you very much. So, you can contact me. So, if you have any question, you can write back to me. So, I will try to reply in future also. Thank you.